Battery Management System, or BMS, ensures safe, efficient, and long-lasting battery operation. It regulates charging and discharging, balances cells, and monitors temperature to maintain proper operations. But how does a BMS make split-second decisions to protect the battery and optimize battery performance for extended operation? Let's find out as we dive into the exciting world of BMS Electronics. BMS Electronics typically consists of several integrated circuits, or ICs, working together to maintain battery health and efficiency. These functions include sensor measurements, charging and discharging, safety and prevention, state of charge, state of health and other state of function estimation, cell balancing, authentication, and communication. Modern battery management ICs, like the battery fuel gauge from Renesas, encompass nearly all of the BMS functions. It embodies a microcontroller unit, or MCU, that serves as the brain of the system, continuously monitoring and controlling the battery's voltage, current, and temperature, and ensuring that each cell operates within the set safety limits, preventing dangerous conditions such as overvoltage or current or undervoltage that can degrade lithium-ion batteries. It does so by disable charging or discharging by controlling the FETs, or by blowing the fuse to permanently disconnect the battery from the pack terminals. The fuel gauge may also perform cell balancing to ensure that no single cell is overworked or undercharged, which may lead to aging. To accurately estimate how much energy remains in a battery, the fuel gauge IC uses advanced measurement techniques such as Coulomb counting and voltage-based algorithms. This feature provides real-time insights into the battery's state of charge and state of health, allowing users to track energy consumption effectively. Over time, as battery degrades, fuel gauge IC also helps monitor the battery's aging process, offering valuable data for optimizing charging cycles and determining when battery replacement might be necessary. In multi-cell battery packs, some cells may charge or discharge at different rates due to natural variations in capacity. Cell balancing ensures that all cells maintain equal charge levels, preventing imbalances that could lead to premature degradation or failure. It can achieve this using two methods: active balancing, where excess charge is redistributed between cells through charge shuttling, or passive balancing, where fuller cells are bypassed during charging. Modern battery systems require seamless data exchange between the BMS and external devices. The communication interface are typically SM-Bus, I2C, or SPI for short-distance communication, and CAN, UART, or Ethernet for long-haul. They allow the fuel gauge IC to report real-time status updates, error messages, and performance metrics, making battery systems smarter and able to integrate with advanced analytics platforms. As you can see, each of these BMS functions plays a crucial role in ensuring battery safety and efficiency, and modern fuel gauge ICs integrate most, if not all, of these functions into one small package, making BMS easy to incorporate into a design. Now, let's explore how BMS electronics may differ for different applications. Laptop battery pack key considerations include safety, performance, longevity, and form factor. The most common battery chemistries are LCO for high energy density and fast charging, LFP for safety and longevity, or NMC for a balance of the two. Common form factors are cylindrical package filled with liquid electrolyte, or lithium polymer cells filled with electrolyte gel, great for laptops requiring a thin profile. Battery packs for smartphones and other handheld portable electronics focus more on compact size, energy density, and fast charging while still maintaining safety and longevity. Most portable handheld electronics use lithium polymer batteries for its thin and lightweight form factor. In laptops and portable handheld electronics, fuel gauge IC protects against short circuit and overvoltage, as well as against undervoltage, which may lead to battery swelling. Fuel gauge can also monitor the battery state of health and guard against counterfeit batteries through authentication. Designing Power Tool Battery Pack 4 requires a vastly different approach. Power tool batteries must deliver high power output, durability, and long cycle life under extreme conditions. As such, NMC, LMO, and LFP are the most popular battery chemistries. BMS and power tools must handle thermal regulation, overcurrent protection, and support fast charging, and enable extended battery life. Designing a battery pack for energy storage systems, or ESS, presents a unique set of challenges. These systems are often deployed in grid storage, renewable energy backup, and industrial applications, where they must sustain performance for decades rather than just a few years. LFP is the most commonly used chemistry for ESS due to its high thermal stability, long cycle life, and safety advantages. LTO batteries shine where ultra-long cycle life and extreme durability is required. Used batteries from electric vehicles often find themselves in ESS applications. These second-life batteries often retain 60 to 80% of their original capacity, but at a fraction of their original costs, making them well-suited for stationary ESS applications. Using the state of health data from the fuel gauge IC to sort out poor batteries is important in second-life applications. Automotive battery packs work similarly as other battery packs, except they have much higher voltage, current, and cell count. The higher cell count necessitates stacking of multiple isolated analog front-end ICs, often daisy-chained connected for communication, back to a common MCU, running at high speed and with ample memory. The MCU together with the AFE form an electronic control unit, or ECU, that is connected to other ECUs in the system over CAN, UART, or Ethernet. The MCU inside the BMS electronic control unit serves as a battery fuel gauge for the system, responsible for monitoring the battery parameters such as voltage, current, temperature, estimate the state of charge and state of health and other state parameters, perform cell balancing, provide thermal management, provide charging and discharging control, and support communication and data logging. Automotive BMS usually have a more powerful MCU that can deploy more complex algorithms, such as electrochemical impedance spectroscopy, or EIS, used to extract parameters of high-fidelity battery model by measuring impedance over a range of frequencies, and can be used to identify aging effects and failure signatures, enables real-time monitoring and predictive maintenance, enhancing battery performance, safety, and lifespan. BMS fuel gauges supports big data by monitoring battery performance of entire fleet of electric vehicles, scooters, even smartphones and laptops. The data can be used to evaluate battery performance, schedule preventive maintenance, actuarial analysis for warranty purposes, and to pre-sort the batteries for second life application. I hope now you see why BMS plays a vital role in the safety and efficiency of rechargeable battery packs. While core BMS functions are generally consistent across applications, battery pack implementation varies. As battery technology evolves, BMS designs will continue to advance. I hope this video has provided you valuable insights into BMS Electronics that have been working behind our modern battery-powered systems and devices. Thank you for watching.